It's great to be here, and it's great to be part of MIT community. I've worked with many of you in different capacities, and I look forward to collaborating with more of the faculty members and the students and programs in MIT. So today's I guess is the first talk of the NanoFab in 2023. So it's my honor and pleasure to be here. And I'm glad we have some attendance in the room, not everybody online, because these presentations online is really doesn't give the speaker at least the full satisfaction of getting feedback from the audience. It's just you're talking to your screen most of the time. So today I'm gonna talk about not knowing exactly what background of audience and disciplines and area of our interest is. I wanted to talk more about what's happening in the semiconductor innovation and how it enables a massive amount of innovation across all disciplines in electronics and electrical engineering across the board. These days, I mean, a few years ago, I had to explain to my family what I'm doing for a living, but now you don't have to do that. Chips is becoming such a popular thing in Washington when president holds a wafer in his hand and all that stuff. So there is no need to talk about that anymore, but also it shows the amount of value and strategic importance of innovation in semiconductor as a geopolitical advantage, as well as the foundation or the bedrock of the innovation for many fields. So my first few slides, I'm going to talk about how, before getting to deep technical side, I'm going to talk about how the innovation in semiconductor is important and how enabling it is and how exciting it is. So let me start with a couple of charts. It's amazing that people thought that the is there a pointer, or should I use, maybe I use just mechanical pointer. It's not, there is no semiconductor in this one, but because this one, yeah, actually maybe this one works too. On this screen, maybe it's not. But anyway, if we thought that a semiconductor or chips in general has seen their peak before, think again, because we see that in the past, the big disruptions in chips was like by one application when mainframe was started or PC and internet started, and then mobility handsets started. But the next one, it's not the one thing that is driving the next generation, everything around you. I mean, I always use example of your doorbell used to be just two metals touching each other. Now there is $35 worth of semiconductor from Wi-Fi and AI and radar and everything around that. Look at the everything around you from automotive. Just give you an example. A typical automotive had about $300 worth of semiconductor in it. Today, I was talking to CTO of one of the high-end car manufacturers in Europe just a couple of days ago, $2,500 of the semiconductor in the car, and 200 clock references, including a chip-scale atomic clock in a car. So you can see the level of electronics that is going in everything around you, and that's what is driving. And of course, data, the fact that you have massive amount of data available and how to process them and how to take advantage of them. Just to give you an idea, the expectation is that this is gonna be $1.3 trillion market. I mean, this is number 3 or 4 US export after aircrafts and oil, I guess. And it took us 50 years to get to 500 billion. In next 10 years, we're going to go to 1.3 billion. So you can see the dynamics of what's going on in semiconductor. And just to give an idea, I was, as Vladimir said, I'm part of this government activities on CHIPS Act. Here is how many organizations the government are involved in semiconductor, one way or the other, from national labs and DARPA and so on. And two areas that are driving innovation today, in addition to consumer electronics. Consumer electronics always tries technologies first because they tend to be more risk taker because the lifetime of this consumer electronics is shorter. But also automotive and data centers are pushing semiconductor to the edge in terms of performance and what we need next. And the fact that without more disruptive innovations, we cannot offer enough machine learning and AI capabilities to handle the data. So here is another chart that I mentioned. An internal combustion is about 300. That was the electric vehicle without ADAS. With the ADAS and machine and autonomous driving, we are talking about $2,000. And interestingly, by 2030, as you know, no new internal combustion car can be produced in California, in Europe, and in China, and many other places. So you can imagine annually about 100 million cars are manufactured, built. If 30% of them or 40% of them or all of them become electric, it's 100 million times 2,000. That's another couple of tens of billions of dollars of semiconductor coming to the picture. So it's exciting. I think the next breakthrough in automotive, in drones, in everything is when the battery technology goes below $100 per kilowatt hour. That is the breakthrough, because then the cost of electric stuff is going to be same as internal combustion. You don't need subsidies. And everything is going to be battery driven, from flying objects to driving to robots on the roads to deliveries and everything around that. Here is a chart that is very interesting to show people who are talking about sustainability and environmental issues. Without semiconductor presence in this grid, our energy usage would have been something like that. And with use of the smart grid, we think that the energy usage, we are going to save about 3,000 billion kilowatt hours by making the grid more intelligent and more semiconductors in the grid. And that is talking about high voltage semiconductors, like I'm going to talk about gallium nitride, silicon carbide, all the way to controls and data and machine learning. Actually, space also is going through a big change. I call it new space, or democratizing space. Remember, satellites used to be like at least a refrigerator size, maybe multiple refrigerators flying over, and huge amount of weight and propulsion. The new ones are mostly running into LEO, low orbit satellites. And low orbit satellites, of course, the advantage is about 500 kilometers, 300 miles up there. So you need a much lower link budget to get a signal up and down. The beauty of that is it's closer. The difficulty is that it's not at the same point, so you have to track it. So you have many of these LEOs running around, so you have to track it, hand it off to the next guy. And so you need a system that can track these devices. I remember for my PhD, I did one of these systems that cost about $1 million. Today it's about $100. And the reason for that is we can put 1,024 phase array beam-forming antenna on a single dish of about 20 inches and have these massive processing power to do this phase array and track these satellites and offer very high data rate. So it's a fascinating opportunity also for those who are working on machine learning and RF. And by the way, another beauty of LEO is that the radiation hardened requirements is much more relaxed than GEO, and that makes it easier, because once you wanted to make a radiation hardened semiconductor, we spend a lot of time in TI. Actually, we have a department doing that, but it takes cost and complexity. So that was the background to get you excited about the fact that chips innovation is driving almost everything in every discipline, not just electronics, but every aspect of our life. But clearly, we need to talk about beyond traditional scaling, because traditional scaling is getting to the point that just by doing the better lithography, you are not going to achieve all the performance that you need, because you're almost at the limits of, the atom per transistor. And the fact that you are limited by other factors, as I showed, that, the number of transistors doesn't mean necessarily higher performance. So the future is even more exciting, because in the past, we always hoped that the next node of the CMOS is going to solve our problem. If you don't have enough speed or enough transistors, or you can't afford so many transistors, wait for 2 years, next node is coming, it's going to solve most of these problems. Then we got to the point that interface became the bottleneck, no matter how many transistors. Now you cannot get any smaller with the same approach of just relying on lithography. Put aside the fact that the typical lithography at 5 nanometer is about $200 to $400 million, and then cost of the designing the system, a typical AI GPU cost about $500 million from the design to manufacturing. So these are massive amount of design investment, and the fact that what's next, and we cannot rely on that one. So what is interesting and what is next is no longer one vector. define in the future is multiple vectors. And these multiple vectors need to work in harmony to create that kind of performance improvement that we expect in the future. So let me give you a couple of examples. On the materials, I think one of the most breakthrough opportunities we are facing is how to come up with materials that, in addition to silicon, not in replacement to silicon, can offer exponential performances. And I have many examples of that. I briefly talk about some compound materials, 2D and 1D, and some metal oxides and other materials that is not new. People have been looking at it. Some of them are, but not all. The point is that most of them don't have the same manufacturability that we are so good at in silicon, and that's where we see for, and we expect that FinFET is going to solve all the problems. So we can see gate all around, complementary FET, bidirectional FET for power applications, and so on. All of these are becoming very interesting device approaches beyond what we are doing. Sorry, I went fast. Okay. So how do we go back? Okay, and I had some animation too. Packaging is becoming one of the most exciting. Packaging, by the way, was one of those areas that universities even didn't bother having a course on it because it was not cool for research. You cannot, it's considered industrial back in the line. But reality is that once we get to the limits of monolithic packaging, and it's not just putting two chips next to each other, call it MCM. Today, in most manufacturings in semiconductor, big companies, there is a penalty for MCM because of a lot of pick and place involvement. You need to do manual, kind of like almost manual. It's not like wafer level processing. The future is how to do packaging in a way that is as efficient and it's not limited by the parasitics, being it or memory or RF source. And that's where, of course, there is a massive amount of investment from government. DARPA has these 2.5 and 3D. Chiplet is becoming now a name of the game. And the beauty of that is there is now some standards being developed for chips to talk to each other. So different manufacturers of different silicons or different semiconductors can integrate it. And one of the most exciting part that I'm going to spend a little bit of time on it is back end of the line processing technology that really are compatible with silicon in the sense that you can do all the processing in 450 degrees and below, so you don't mess with the transistor structure on your chip. You can build new structures back end of the line post metal, and that is something that is very exciting. And also on top of all of that, how to go beyond just von Neumann architecture of processing, just memory processor, IOs, traditional. And there are some really interesting approaches on accelerators that can improve the performance, especially with in-memory computing, that you can do some of the processing within the memory. So you are not limited by the bottlenecks of memory and processor. I remember the first book I read about this, a very interesting book was in 1981, doing this analog signal processing to model the brain. I think today we are in a much better position we don't know still how brain works. So I was wondering how we can model the brain when we don't know how it works. But the point is that can we get the efficiency of the brain processing? I think our brain, depending on the size of the brain, burns about 8 to 20 watts. It's about 2% of the body's weight. Again, varies, for some people are smarter than others, but it burns about 20% of the energy. So extremely efficient, billions of neurons talking to each other at that 8 to 20 watt power. How can we model the same kind of circuits in a mixed signal environment between analog and digital? And of course, last but not least, how to use randomness of quantum to model random things in life. We're dealing with a random world. I mean, random everything around us, from the weather forecast for tomorrow all the way to drug discovery and everything around that. So if the randomness is built into the world around us, how can we take advantage of randomness of quantums to model this without going through zeros and ones? And that is the beauty of that, except that you need cryogenic situations. So that's the area that we see a lot of research going forward. I love this term, this quote from Heisenberg, one of the founders of quantum mechanics. For us, we spend a lot of time looking at periodic tables, see which element is going to help us to do the next big thing in transistors and switches and power. And he says that don't worry about it because they are not real. They form a world of potentialities. That's what quantum language is. And the possibilities rather than the facts. So that is interesting. I mean, but I take it in this talk more metaphorically. I'm not going to use that as non-real stuff because we have to build them. Vladimir can tell you, and have nanofab for that. So, but the reality is that the amount of technology and materials that we need for these technologies are amazingly moving fast. Let me give you an idea. When in 1985, that was about 30 years or so after transistor was invented, these are the elements of periodic table we use for semiconductor. Here's what we're doing today in semiconductor. Almost half of periodic table is being used one way or the other in semiconductor design. And it's not just silicon. I mean, silicon is there, but not just silicon. And all of these, by the way, need to be manufacturable, because if you're dealing with 1 trillion parts, they have to be reliable. And you need to make sure yield and manufacturability is high. So we already are occupying more than half of the periodic table. And I wanted to emphasize a couple of them for the sake of discussions we have today. So what are the silicon plus opportunities that in the future, near future, I'm not talking about 10 plus, I'm talking about next couple of years. Silicon germanium has been around for a while, a compound material. We see tremendous opportunities on SOI for RF and for photonics. You know, in photonics, silicon can go so far, about 900 nanometer wavelengths. After that becomes transparent. So you need to go to germanium. And then the question is how to deposit germanium on silicon to optimize it for photonics, at the same time relax the alignment of the fiber optics to the device. So these are IO plus performance and plus the fact that you can integrate multiple devices. By the way, for RF also, silicon germanium today can offer performances that in the past was only for 3-5 materials like GaN and gas. Of course, GaN and gas have also made a lot of progress. 3-5 materials, I missed one. I just want to make sure if you notice. It's 3-5 materials. These materials have been around on different substrates. In fact, small wafer size 4-inch GaN substrate, GaN on GaN substrate has been around in used in defense quite a bit. What we see is a huge difference is that now GaN on silicon takes advantage of the productivity and cost advantage of silicon processing, but using GaN on the as a device on top of that. And of course, AlGaN and the epi that you need to grow to buffer the device from the substrate, 2 different materials. Also, silicon carbide, gallium arsenide, indium phosphide, they have their opportunities to impact a lot of technologies, especially when it goes to terahertz technology, high power. I don't know if you have seen some of the updates on these massive now, because when you go to terahertz, hundreds of terahertz, the path loss is very high. And you may complain why you have so much path loss. But the beauty of that is when you have so much path loss, then by nature, it's secure. You cannot tap into that because attenuation would be very high. So now there is some advanced projects to have these drones in the air, massive number of them that can talk to each other in hundreds of terahertz. And these are by nature more secure, but then you need to have some power, and these devices, especially GaN for power amplifier as well as for power switches, is very exciting. So, and also on power management, we see that GaN, especially GaN, is a game changer. And the reason for that is power devices don't benefit from scaling necessarily. In fact, sometimes they don't need a scaling, or they can't scale because you need the voltage and power density. So obviously, when you don't scale, then your switching frequency would be limited, because now you're dealing with the nodes that are not switching or high speed as high speed as digital nodes. That's where GaN comes to the picture, because GaN, you can have higher electron mobility, switch at higher frequencies. And when you switch at higher frequency, what's the first implication? Your passive devices are going to shrink, and the power density is going to increase significantly. So that's why we see that GaN is already there. In fact, I was in Best Buy. See, there's a section says that GaN inside. I mean, that's very interesting. So I think so. It's no longer just a research part, but we need to do more to improve the power density and possibly voltage, and integrated with drivers and the rest of the system. Silicon carbide is now the main power device for anything kilovolt and above, and we see that automotive is a big driver of that. I don't know if the topic is hot or the temperature. So do you want to, I mean, is there a problem there with the temperature? I think because it's a little bit too hot. And yeah. And also photonics on silicon, bringing more photonics closer to silicon is becoming a big deal, because of the fact that almost the data rate that you get out of the chip to chip, or board to board, or rack to rack, almost we are running out of steam when it comes to copper. And the fact that now you're talking about 400 gig and beyond, photonics needs to get closer to silicon, and that's where we see some technologies like indium phosphate and others are very important. And metal oxides is another area that aluminum oxide and many other oxides that people are looking at for power devices and higher density power devices. So you see that massive number of technologies and devices that can offer performance beyond silicon. Also 2D and 1D material. TMD materials, molybdenum sulfide, deselenide, and tungsten and platinum, they show some amazing performances. I'll talk about that later. Still, it's a very researchy topic, but we think the beauty of that is you can build it on top of CMOS. So you can have your own chip, it doesn't matter what technology, and on top of that, you build a structure for RF or other sensing modalities that you wanted to address. And we see the performance is quite promising, or even technology like CNT. CNT has been around for quite a while. I think we need to look at CNT in a slightly different way. CNT, if you expect to use CNT the way that you are using silicon today, how long has it been that we're looking CNT? 10, 15, 20 years? Not manufacturable, not as manufacturable as silicon and other technologies like silicon germanium. But there are new ways to look at CNT. I'll briefly talk about that to plant the seed. But the fact that purity and reliability and performance in the CNT should be looked at differently from just traditional silicon, and you have to look at it more statistically. So it's statistical reliability, not just kind of perfect reliability. And that lends itself to some applications that can really benefit from high electron mobility of these devices. Also for sensing and passive devices, building MEMS materials on top of silicon. I'll show an example of that. Adaptive materials, these are metamaterials that you can really engineer them in a way that they can have special properties for sensing applications, and also for RF applications. So you can see that the domain of innovation is much bigger than just one material and one approach to device. The challenge is that when you have so many vectors, obviously you dilute your resources to support all of these. How do we do a different approach to device design so that it's manufacturable in less than 10 years? Because history shows that a lot of these new devices, you can show one sample in the lab, publish a great paper, it takes another 10 to 15 years before it becomes manufacturable. So that's a topic that would be very interesting to use machine learning to model some of the manufacturing problems early in the game and see how we can benefit from new approach to material discovery. So here is the chart. This transition metal, let me see if I can spell it one more time, like dichalcogenide materials. And these are like combining this column. Look at the performance. This is bulk and this is the 2D. Some of these are better than silicon, and some of them, even 1D carbon nanotube is almost the performance of gas and indium phosphate. So you can see that electron mobility, carrier mobility is quite promising. And it could be a back end of the line process in many cases. The question is, can we make it reliable enough to offer as a, and that is the beauty of this, what I call it, next generation heterogeneous devices. That doesn't mean just, that is beyond wafer, of course, wafer bonding, die bonding, nano TSVs and all that stuff are important. But here is more like one step beyond that, looks even very promising and exciting to combine this. On the integration and heterogeneous integration, chiplet is now the name of the game because you have to bring different technologies together for performance, for applications that you're looking at. And there are some advances on wafer bonding, die bonding, monolithic 3D, interposers. I mean, you're familiar with all of them. I think there's going to be more of that. But more interesting research part is related to how to do post-CMOS fabrication so that you can benefit from scaling at the same time, add more functionality on top of that in a low temperature, below 450. So let me give you a couple of examples of BOL that was very exciting and is exciting. This one, we did it in TI many years ago. It took us much, much longer than expected, but it's amazing. That is like a DLP, or a digital light processor, which is really totally post-CMOS. So we take any CMOS-based CMOS, and we build a structure on top of that. Just to give an idea, 2 million mirrors on single chip, each mirror independently moving with billions of cycles reliability. Well, if there is a projector here, most likely it's doing that. So these are like a lot of issues and with restrictions and all that, but everything can handle it with pretty much CMOS compatible processes. And these 2 million mirrors can interface with the processor under that to achieve a combination of advanced MEMS processing and AI machine learning. To give you an example, we challenged some of the researchers in another university that can we use this to create some unique capability of the headlights in the car. So headlight today or in the past was one beam, one light bulb, one beam. By using DLPs in a headlight, you can create 64,000 independent beams. Each beam can go in a direction on the sign, on the road, on the pedestrian, whoever. But one challenge is that, can we do something even more fancy? Can I improve the vision of the driver in a rainy condition? We call it technology for rainy day. And the unique is that you have to detect the drop of the water and steer the beam in a different direction. And you think it's not possible. So I have a video that we did it. Let's see if I can run this video. So here's a DLP on each headlights. We detect rain that is coming and steer the beam around that, so you don't see the rain as much. So you can drive safely. Can I stop it somehow? So here is the projection of the arrows on the road. So you don't need to see the arrows on your GPS. GPS is going to be on the road. But here is the situation. It's rainy situation. So we detect each drop of rain and cancel it. So there's no rain now. So that shows how much real-time signal processing and machine learning you have to do. And by the way, these are 3D stuff that we do with the same technology. So you don't need a screen, so many screens in the car. It's like the holographic screens that you can have any area in the car. So the number of I don't remember exactly how much GPU processing power we needed for that. I can dig it out in my slides, but you can imagine for that kind of processing, you need a massive, massive GPU or uh, processing engine, and you need a massive number of MEMS, and they need to be highly coupled each other because of the interface limitations. You cannot have it on two chips. And here, back end of the line kind of processing of this technology, 2 million mirrors on top of this managed to do that. And that is the complexity of real-time processing, because there is nothing more real-time than rain, right? I mean, or kind of the way that it's going around and randomness of each drop. So another example of is that what's happening in the, what we call it, medical field. We can have now massive array of medical sensors all built on top of CMOS with some variation of ISFET, ion sensing FET, that can detect, or it's like open gate transistor, and the ions, I mean, it's like a pH detection. So you have a polymer, a pathogen sits on top of the polymer, changes the pH, and then you translate it to voltage. So it's pH per volt, pH variation per volt. Now you can have massive number of these transistors, a single chip. You can detect all kind of pathogens by back end of the line polymer printing on top of that. So you can imagine, I don't use lab on a chip because it has a bad connotation these days because of what happened in Silicon Valley, but it's going to be type of like chemical sensing. Chemical sensing is massive number of chemical sensing, could be hazardous materials, could be. So you can see all of those big machines or functionality of big machines can be in a small device. Here is what DARPA published as far as the target performance for powered FETs for RF. And you can see that we have a long way to go beyond what today we can offer. Of course, silicon germanium is a big player. We can see that indium phosphate and gallium nitride are going to be a big technology of choices on this one. And RF CMOS now is limited by power, and of course limited by the fact that you need to have enough voltage on top of the device to get the power out of it. So I just put by CMOS and CMOS, but you can see the 3-5 materials are playing big deal on this to get to the performance that defense and aerospace need. Another one is metamaterials. As I said, metamaterials today, there is a project that, you know, in the smoke detectors today, just detect smoke, right? I mean, with this LEDs and, you know, reflections of LEDs. But now in the future, you want to detect the particles that you have in the chamber. And that's where the metamaterials, you can process the surface of the silicon or create these resonators with different resonance frequencies. They react to different chemicals. We also have a spectroscopy in every smoke detection. You can detect the material and the gas that is coming to the chamber. And these are very affordable and very compact. So in order to have this kind of material research going, we need new tools. That's why we have nanofabs. You know, and these new tools are amazingly powerful today. I mean, the way that semiconductor industry for last 50, 60 years has driven innovation in tools, in EDAs, in materials, in devices. Its whole ecosystem is fascinating. I don't know any other fields of the science in humans history to have this kind of ecosystem innovation across the board to create a situation that you can have so much performance at so affordable cost. So the machines that we are very familiar with, of course, lithography. Lithography is, I don't know if you have seen these machines, the latest one, it's almost size of this room, maybe it's not bigger. But what I was shocked about is that the mirror can only afford 1 picometer variation in the height, 1 picometer. So if I put a matchbox stick on the face of the earth, that's too much. variation. It cannot be like that. So you have to polish the surface of mirror to get that kind of picometer smoothness to achieve below 2 nanometer lithography capability. But not everything can rely on these couple of $100 million machines. Plasma etching is becoming a big deal for some of these high aspect ratio post CMOS processing. And they have come a long way, very exciting and not as expensive. MBEs for growth of novel materials. Now I read a report on last year, there is a new MBE with the laser that pretty much you can play with the angstrom of the depositing new materials. And that is slightly expensive than plasma etching, but not that much. So these are tools that really powerful. ALDs, ultra thin, few nanometers of oxide or nitrides depositing, and AFM, which used to be just observation tool, now you can manipulate atoms one at a time, pretty much. So that kind of resolution, that kind of capabilities enables us to look at these materials and some exotic proof of concept like maskless lithography or even printing. Printing now you can get a resolution of less than 1 micron. That is with 1024 nozzles. So you can do a lot of stuff on this thing. So you can see that all of these are opening new doors, but we also need to add to that some manufacturing prediction or capabilities early in the material discovery, because as I said, when it comes to yield and throughput and manufacturability of these materials, a lot of surprises show up when it comes to volume manufacturing, and that's where we wanted to use some of these machine learning algorithms to see we can preempt some of those manufacturability issues early in the game. So my message is that more innovation in chips will enable innovation in every other discipline, not just electronics, not just EECS department, but everything from sustainability to healthcare crisis to everything around us. And I think it's just the beginning. Thank you for your attention.
Ahmad, thank you so much for an amazing talk. The floor is open. Those of you who are online are more than welcome to send your questions via the Q&A button on the bottom of your Zoom screen. I'll make sure I go and read them. I will, to start us off, I will open the floor to the audience in the room. Please raise your hand. Ahmad is here. He can answer any question that you pose. I'm very much sure. Yes, let's start.
First, thanks. This is a kind of a journalist question, I guess. There were 3 areas where I found myself wondering, so how are you going to be able to do this? One was materials. Where are the materials going to come from? Second was, where's all the energy going to come from? I mean, you're talking about reducing power density, but like there seems to be a lot of power and energy implicated in this. And then the other thing, when you talked about the drones, I was thinking, what's the FAA going to have to say about that? It seems like, we're going to fill, space with drones.
Yeah. So I need to give you a journalist answer or research answer. I mean, either way. Yeah. And the materials, actually, the downside of it is the most expensive part of innovation is materials, because it takes longer. And as I said, taking it from lab all the way to fab is a relatively long journey. Just to give you an idea, for us to get so good at CMOS, it took us about 3 decades for the entire industry to make it so high yield, high reliability, manufacturable device. For some of these power devices like GaN and others, almost 2 decades. So we cannot afford to have this kind of long, because that means a lot of waiting stuff. So on the funding side, I was talking to Vladimir about that. That's where universities and government funding, because in the past, a lot of material research was in places like Bell Labs, unlimited budget. When I was there, it was like you can work on anything, and once in a while you hit germanium and make a transistor out of it. but now we need to have a situation that under more realistic way with government, with universities, and with pre-competitive, that's the key, pre-competitive research, we handle material part of it, but also on technical side, we cannot do the same way of material discovery in the past that we get super excited by one-off material, because at the end of the day, you're talking about 1.3 trillion parts a year type of semiconductor industry. So you need to look at manufacturability early in the game. How? That's an interesting open question. And I mean, there are some ideas and I have some ideas, but it needs a lot more work. So yes, material is the big part, foundational, most expensive, and most critical. And I think we need to do that in a different way, especially with all these machine learning capabilities and forecasting, chemistry and physics of materials and all that stuff. On the energy side, obviously, if you have 100 million cars electric, each car is going to have about 100 kilowatt hour battery. Multiplied by that, that is going to be a few power plants that needs to be gigafactories for the batteries. So I'm quite optimistic about energy, because on the consumption, we have made a huge progress as far as efficiency. You saw the smart grid chart. We are saving a few thousand billion of the kilowatts of the power. But on the generation also, other than solar and wind, that always going to be a part of the game, there is a massive amount of research today on fusion, as you heard, and fusion has been always the technology of tomorrow. But now we see that startups with fusion technology working. So I don't think it's around the corner next year, but with announcement just before the holidays, right, in Lawrence Livermore, it's doable. The problem is they spend 300 megawatts to create 300 kilowatts of power, but that was because of the laser inefficiency and all that. But the fusion is doable. And there are some fascinating ideas. I've been talking to some of those, and it's quite impressive. And of course, fission is always there. Fission, I know that environmentally people are questioning that, but now there is a wave that they're saying that's one of the cleanest. In fact, if you find a way to handle the waste, and there are a lot of discussions there. So I think on the energy side, we are getting much better to semiconductor on the consumption, and on the production, there's some promising technologies on the horizon. Okay.
Other questions? Yeah, Mark.
So you talk about the angstrom age, and you talk about very short channel lengths or device sizes, right? And then you also talk about manufacturability and the problem of the path to manufacturability. So how do you see things working out when in the lab we can do stuff with e-beam lithography, direct write, with throughput that's hundreds of thousands of times slower than manufacturing, and most of which is not happening in the US in terms of length scales below, what, 20 nanometers?
Actually, today, I mean, there's factories in Arizona and others made for 5 nanometer and 3 nanometer. So that's exactly my point. You can prove the concept with MBE or with some, maskless techniques that you wanted to play with this only material. And that's a big step to show that it's doable. You can get the performance. The big question is that, and that's a separate research topic, that what's the manufacturability capability? Because in the past, it's like we put it in the flow and then we see what's not working. And if we have full flow here, and then we give feedback here. That model served us well if you have infinite time and budget. Today, just to give an idea, if your data usage is going 20% high in 1 week, you need a lot more processing power and power density and high-speed interfaces in a matter of years, not decades. So how to make it manufacturable here? I'm really glad the awareness of chips strategic value is here now, and so we're going to have capabilities to do that. But even that requires a machine that you go to a couple of $100 million of lithography. And mass cost, exactly. Mass cost is very big. Mass cost is staggering high, in fact. So that's why we need to have a way that you can share some resources to explore these new ideas. But those days of, okay, I proved the device under MBEs and now you make it manufacturable is not going to work. it has to be a tighter loop around that. What's the answer? I don't know exact answer, but it has to be different.
Thank you for the talk. So I have a quick question and a more sciencey one. The quick one was I noticed gold and silver were part of the elements that are used in CMOS now. It's kind of surprising.
Yeah, gold or silver is very important for medical applications, inert materials. So they want gold so that these ions and chemicals don't interact with passive. I mean, it's a passivation for medical, really. So
it's like,
yeah.
Okay.
And by the way, some of the eutectic wafer bonding also using gold because of the fact that they can create a very special bonding between two wafers.
I see.
So we don't use gold unless we have to.
Okay. Yeah. The more technical question was the video that you showed of where you have a car and it's driving in the rain. So is the correction happening by the DMDs or it's happening on the screen? What you're seeing is being corrected.
We have two versions. So version is that on the screen we regenerate the image. Also, we're working on kind of steering, and these are all experimental. It's not like steering the beam around the
Steering it or like phase conjugate.
Phase conjugate, pretty much. Yeah, exactly. It's like phase array.
All right, question in the back.
Thank you so much for the talk. One question I have is, how much work has been done and where do you think work will go in terms of using biology to generate products and chemicals and other things like that? Because we've been using animals and plants forever as factories. So perhaps there's something we can do on a nano scale, but more with more, shall we say, practicality in terms of getting things to do exactly what we want. It's one thing that we don't really know how the brain works. Actually, we know a fair amount about how the brain works. We know very little about how the mind works. So you still have a lot of luck over there.
Yeah, absolutely. Yeah, actually, on the first question on biology, there are two aspects of that. It's one of the most exciting aspects of semiconductor applications. There are two angles to that. One of them I'm more familiar with, and the second one less familiar, but I have some exposure to that. First is the biological sensing modalities. That is becoming very practical with some of these new polymers and metamaterials that you can deposit on silicon to offer a massive array of sensors for biological pathogens or any molecule. I showed it. Let's see if I can go back to one of my slides. Single molecule detection that we are working on with some. Oh, sorry, maybe I'm going wrong way here. Let's see. Okay, this one here. Yeah. So really here is that like with this ALD deposition, we can have this monolayer surface functionalization to detect a single molecule spike on some of these receptors. So in other words, the semiconductor is sensitive enough, can detect the variation of the pH with single molecule. It's like single photon detectors in the APDs. Now we're single molecule biological. So that part of it is going really fast and exciting. And also there is tremendous amount of work how semiconductor works inside the body. And that is another area that is picking up quite a bit. So the sensors or therapeutic aspects of semiconductor, we see tremendous opportunity within next 10 years to the point that you can have a lot of therapeutic and medical work on sensors on the body or minimally invasive, like under the skin with microneedles. I think there is a very successful part today in the market that we worked on it for quite a few years. It's a glucose meter that can every 10 minutes gives your glucose reading. It's microneedles. You don't even feel it on a Band-Aid. It's Libra. You can buy it in pharmacy and with a prescription. And you can imagine tomorrow you can give potassium, which is important for some of these kidney and dialysis. We can have other chemicals detection, because once you get under the skin, literally, that you can have a lot of capabilities to offer this biological sensing. So that part, I think we see huge variations. There is another aspect of convergence of biology and semiconductor, designing transistor in a petri dish. That part, still I'm holding my breath there. I mean, I don't know, I think because we are trying to figure out how to use biological interactions with, to create a semiconductor like amplification or switching. It's way out there. I mean, that's my assumption. I think maybe I'll be happy to be surprised by progress elsewhere. I've seen a lot of work that one, but on semiconductor, we don't know some of the quantum go to the biological material. That's a very complex. So that part of now. On the brain side, yeah, I mean, I need to be mindful about the brain. You said mind is, so mind, mind or brain or conscious or whatever we call it. We had a project with some really good neurobiologists, and the way that signal processing happens in the brain seems to me is still an enigma. How these spikes creates without any A to D and D to A, you know. I mean, one of the fascinating, I'm an engineer, so I look at biology from engineering. These hair cells in the ear that, you know, they have stiffness. So when the air hits the ear, they do FFT based on the stiffness and then send the FFT signal to brain with the reduced complexity. So a lot of data compression and stuff is happening. I need to read more about biology to understand how it goes, but and study more of that. But these are two different aspects and two different timelines from my viewpoint.
So I'm going to just commandeer the questions because time is running short. I want to pass a few questions from online.
Sure.
First one is the future of transition metal oxide materials in the future of electronics. Similarly, topological materials or materials having a spin. What is the likelihood of seeing those in short term available in technologies we're going to be using?
Yeah, as you know, there is a lot of good work there. I have a slide, and it's not my presentation, but the number of papers published on this transitional material over the last few years has exponentially gone up. There is a lot of centers spending time on characterization, which is very exciting. The part that is missing, really, as I said, is manufacturability aspects of it. So I think a really cool university project would be how to preempt or how to predict some of those manufacturers early in the game while we are doing it. Because as far as maturity of research on the device itself, we see that it's very close. But as far as manufacturability, I think we have a lot of work to do.
And I assume the similar answer is for topological materials?
Topological. The one opening for that is, let's use CNT as an example. CNT, 10 years, 15 years ago, we've seen massive number of papers on CNT. People used it for logic and memory. And then the question was, is it manufacturable? Is it worth it and all that stuff? Maybe we should look at those materials in a different way when it comes to yield and reliability. I'll stop there because there is some really interesting stuff going on.
All right, then allow me to ask the very last question for the afternoon. You have presented many, many different technological advancements. They are leapfrogging over the possibilities of what silicon can do today. What's the likelihood that with what the CHIPS Act is offering to the United States to reimagine ways of using such technology to truly do a leapfrog? What's the likelihood the US will actually be in a position 5-10 years from now to, again, reassert dominance in the entirely new way of thinking what microelectronics is?
That's a very good question, Vladimir. I think, let me answer it this way. If we don't make that leapfrog progress, we are going to hit the wall as far as performance we need to run the economy that is based on data and intelligence and autonomous system. Literally, we're getting to a point that you cannot handle the power, the processing, the interface. So it's not a luxury, it's a necessity. We have to do it. And usually we are very good at when it comes to Sputnik moments, okay, if we don't do that, we are going to fall behind, we are going to lose. It's going to hurt the entire economy. I mean, if you can imagine, we cannot offer a semiconductor for data centers that can 100,000 times have more data processing power, automotive that can have higher power density. So, and as you know, it's one thing that we do research for the sake of research. Another thing that if we don't achieve that performance, we are going to hurt the economy and to some extent strategic political advantage. So I think the level of awareness is there, and because of the criticality of this thing, we'll see.
On that note, let's thank Ahmad one more time.